Okay, so now that we have this cosine and cosine, we basically know a lot about them. So before we keep on doing more stuff, let me actually introduce to you, in fact, 4 more trigonometric functions. Okay, so there are a total of 6 trigonometric functions, but the basic ones are sine and cosine, because the other 4, they just come from cosine. Okay, so now that we understand sine and cosine, then we can easily define the other 4 trigonometric functions. So let me do that. So that's what section 5.3 is about. These remaining trigonometric functions and the relationship that they have with each other and so on. Okay. So again, the setup is going to be the same. We are working with the unit circle. So let's suppose that you have any angle. Let theta be any angle with corresponding P, with corresponding point, corresponding P, which is equals x comma y on the unit circle, as usual. Right? So let's draw a little picture. Let's say that here we have our unit circle, and then let's say that we draw our angle theta somewhere in here. This is theta, and then this is the point P, which has coordinates x comma y. So as you know, x and y, we already have names for those, right? So x stands for cosine, y stands for sine. But actually, we don't need to really stop just at looking x and y. We can actually look at all possible ratios that we can make with x and y. So let me write that down. So there are 6 possible ratios that we can write. There are 6 different ratios. In other words, we're going to start making fractions with x and y's, and also the number 1. Okay, so there are 6 different ratios that we can write. Using the coordinates of P. Using the coordinates of P, and those ratios are the following. For example, we can write x. Of course, we can write y. Right? Remember, x stands for x over 1. Y stands for y over 1. Then we could do y divided by x. Then we could also do x divided by y. And then we could flip the x, so 1 over x. And then we could flip 1 over y. Okay? So these are all the possible ratios that we can write. So given the point P, given an angle theta, you get your point P on the unit circle. It has coordinates x comma y. That we can write these 6 ratios. Okay? Remember, x, you can think of it as being x over 1, and y as y over 1. Okay, so each of these guys are names, and each of them corresponds to a different trigonometric function. Okay, let me just write that definition. So the observation here is just like before, that all of these ratios are functions of theta, right? Because if you change theta, P is going to change, so x and y will change, and therefore the is going to change. Okay. So all of these ratios are functions of theta, as we saw before, are functions of theta, just like for sine and cosine. In fact, sine and cosine, they are ratios, and they have names. Give them a name. So definition. So we already know the name of x. We already know the name of y. And now we're going to give a name to y over x. We're going to give a name to x over y. We're going to give a name to 1 over x. And we're going to give a name to 1 over y. Okay? So x we know is called cosine. We call it cosine of theta. Y we call it sine of theta. Just putting this, for completeness. We already know this. Now the new ratio y over x, we call this tangent of theta. Tangent of theta. X over y, we call it cotangent. cotangent of theta. 1 over x, we call it secant of theta, and 1 over y, we call it cosecant of theta. The notations that we use are the following. You already know cosine, you already know sine, then tangent, it should not come as a surprise. We use TAN, abbreviated for tangent, then cotangent, we use COT, abbreviated for cotangent, secant, we use SEC, abbreviate secant, and then cosecant we use CSC. So these are the 6 trigonometric functions, and then it should be clear what's the relationship among them, okay? Which are actually what we call the fundamental identities. For example, we know x and y, those are sine and cosine. So by looking at this, how do you understand tangent? Well, this is y over x. In other words, tangent is sine over cosine, right? Because y is the sine and x is the cosine. Similarly, cotangent would be cosine over sine. Secant is 1 over cosine, and cosecant is 1 over sine. So let me write all of this down. Notice that everything really depends on sine and cosine, okay? So to understand the other functions, you just have to remember these identities. So remark, so these are called fundamental identities. So fundamental identities, they are the following. We usually group them in, we put them in 2 groups. We have the quotient identities. So the quotient identities. And then we have the reciprocal identities. The reciprocal identities. Let's see, the quotient identities, there are 2 of them. That's the fact that tangent of theta, we can write it as, remember, tangent is y over x, y is sine, x is cosine. So tangent is sine over cosine. And then cotangent, that's x over y, so that would be cosine over sine. So those are the quotient identities, and then the reciprocal identity is the fact that notice that if you flip cosine, you get secant. If you flip, we were on the same page, Emily. The same thing happened to me. Don't worry. So if you flip sine, then we get cosecant. And notice that if you flip tangent, what do you get? What happens if we flip the tangent? Tangent is y over x. To find the reciprocal, what do we obtain? We get cotangent, which is x over y. Okay, so those are the reciprocal identities. So let me write them down here. So we have sine, cosine, tangent. What's really interesting here is cosecant, secant, and cotangent. Is the fact that cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. When you flip them, you get those. And of course, the other way around as well. If you flip the cosecant, you're gonna get sine. If you flip the secant, you're gonna get cosine. And if you flip the cotangent, you're gonna get tangent. But usually, when we talk about the reciprocal identity, we usually think about these 3 right here, right? Okay, so questions? You guys understand this? It's just definition, basically, just like sine and cosine, there are 4 more. And as you can see, they all come from sine and cosine. So if you understand sine and cosine, you will understand all of these functions. In particular, you will know all of these values. Are you okay with this? All right. So then let's do an example. Let us complete the table for all the angles that we know already. So complete the table. Complete the table. And let's see, I'm going to put here the angle And then this time we have 6 functions. So we have sine, we have cosine, we have tangent, then we have secant, we have cosecant, and then we have cotangent. And then the special angles. So all the angles that we have disclosed so far. So in other words, you need to know this table that I'm writing. The point is that you don't really need to memorize the whole thing. There is just a few things that you just have to remember. So 0, which is the same thing as 0 in radians. Then we have 30 degrees. So I'm going counterclockwise. Which is the same thing as pi over 6. Then we have 45 degrees, which is pi over 4. Then we have 60, which is pi over 3. And remember, with these three guys, 30, 45, and 70, the other one, so no need to worry about that. And then we have, the special, which are the quadrantal angles. We had 0 over there, now we have 90. Then we have 180, which is pi. Then we have 270, which is 3 pi over 2. And notice that I'm not going to write 2 pi, because if you put 2 pi, that's the same thing as 0. Okay? Because 0 and 2 pi, they are coterminal. All right, so we have this, and now we want to write down the sine and the cosine of all of these angles. Okay, so let's fill in this table. So first of all, let's worry about sine and cosine, because that's what we have done already. So the new ones are the ones that we have after. Okay, so let's see. Let's do the coterminal, the quadrantal angles first. What's the sine of 0? Remember, 0 degrees, that corresponds to the point 1, 0. Sine is 0, cosine is 1, right? Let's go to 90 degrees. 90 degrees corresponds to the point 0, 1. So the sine is 1, the cosine is 0. 180 is negative 1, 0. So the sine is 0, cosine is negative 1. 270 it corresponds to 0, negative 1. So the cosine is 0, the sine is negative 1. Everybody okay with the quadrantal angles? I mean, this is what we did already last time. Okay so far? All right, so now let's put the special guys, 30, 45, and 60. So that's 1/2, and then square root of 3 over 2. And here we have square root of 2 over 2, square root of 2 over 2. And then here we have the square root of 3 over 2, and then 1/2. Okay? So the point is, right? So the point is that in this table, all you really need to remember are these top 2 rows. Okay? Once you know the top 2 rows, then the others you can get it by using the corresponding identities. So you only need to know what we have on red. Now, what I'm writing blue, you can deduce it on your own. For example, to get the values of tangent. What do we know about tangent? Tangent is sine over cosine, right? So let's see. What would be tangent of 0? 0 divided by 1, so that's equal to 0. What's tangent of 30? That's 1/2 divided by square root of 3 over 2. 2's cancel out, so you get 1 over square root of 3, which if you rationalize, you get square root of 3 over 3. 45, the sine and cosine are the same, so when you divide, you get 1. So tangent of 45 is 1. 60, square root of 3 over 2 divided by 2. The 2's cancel out, so because the 1/2 becomes a 2, so you're going to get square root of 3. Right? Then tangent of 90, that's going to be 1 divided by 0. As you know, that's undefined, not divided by 0. So the tangent of 90 degrees does not exist. Tangent of 180 is 0. Tangent of 270. So, wait, what's the problem here? 270. The sine of 270 is negative 1, and the cosine is 0. And then the tangent here does not exist. Questions on how I figure out the values for tangent of all of these guys. Again, just using the fact that tangent is sine over cosine, all right? So now let's fill in the rest. Secant is 1 over cosine, so we just have to get secant, we just need to flip the cosine row. The row for cosine, we just flip it and you get secant. So flip the 1, you get a 1. Flip this one, you're gonna get 2 over square root of 3. I'm not gonna rationalize, just gonna leave it like that. Okay. Then you flip the other one and you get 2 over square root of 2. This is worth writing it down, so this is just square root of 2. So that's square root of 2. Flip 1/2, so secant of 60 is equal to 2. You flip 0, it does not exist. 1 divided by 0. So secant does not exist here. You flip -1, get -1, and then you flip 0, it does not exist. Now to get cosecant, we do the same thing, but we flip the sign. Remember, cosecant is 1 over sine. So flip 0, does not exist. Flip 1/2, you get a 2. You flip square root of 2 over 2, as we saw above, you get square root of 2. Here you flip square root of 3 over 2, so you're gonna get 2 over the square root of 3. Here you get 1, does not exist. And here you get -1. And finally, for cotangent, you can either do the quotient cosine over sine, or easier yet, you can flip the tangent row, because remember, cotangent is 1 over tangent. So you flip the 0, does not exist. Flip 1 over square root of 3, square root of 3, 1. This is 1 over square root of 3, or root of 3 over 3. Now, does not exist. So what do we mean by flipping does not exist? Well, I don't know. So let's look at the other version. Cotangent is cosine over sine, so 0 over 1, 0. Okay, now flip 0, does not exist. And then another does not exist. So we go to the other identities. Cosine over sine, 0 over -1. That's it. So I'm doing this just to show you that as long as you know sine and cosine, then that's it. You can come up with the other 4 guys by using these identities that we listed here, that they are the definition, really, of those functions. Questions? And and everything, basically everything that we have discussed applies now to these 4 functions. So let me write that remark. So remark, and all the results from sine and cosine extend to the other 3 functions. In other words, the reference angle business, all of that extends to the other trigonometric functions. The coterminal angles, that they have the same value at coterminal angles, etc., etc. All the results from sine and cosine extend to the other trigonometric functions. In particular, now we can write down the sine, and then I'm going to close with this. So sine of all trigonometric functions, depending on the quadrants. Trigonometric functions. So let's see, here, let's say that here we have our quadrants, right? So here we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. So I'm going to write who is positive here. So let's see, quadrant 1. Who is positive in quadrant 1? If both are positive, sine and cosine, and the other functions, remember, they are ratios of sine and cosine, or some version of this. So if sine and cosine are positive, then everybody's positive here. So all are positive. You understand this? You guys understand this? In quadrant 1, everybody's positive. Now, in quadrant 2, who do we know is positive? Sine is positive. So What else is going to be positive in quadrant 2? It's going to be cosecant, because if sine is positive, then 1 over sine is also positive. Notice that the other 4 functions, they all have a cosine. A cosine is negative, okay? So the only one that will be positive here is sine and cosecant. Similarly, in quadrant 3, the only function that's positive is tangent, because both sine and cosine are negative. So when you divide sine by cosine, you get tangent, the negative is gone. But if tangent is positive, so is cotangent. Okay? And then in quadrant 4, the only one that was positive was cosine, therefore secant is also positive. The rest are negative. Do you understand this? Right? So I don't know if you know the mnemonic. All students take calculus, and that corresponds for this. The word all has to do with quadrant 1. So yes, all students take calculus. This is just a way to remember this, okay? So all means, everybody's positive. Students begins with an S, so that tells you the sign is positive in quadrant 2, and therefore you can deduce that cosecant has to be positive. Then take begins with a T, so that's tangent, okay? And then calculus begins with a C, that's cosine. So that's what people use, it's something just to remember these things, all right? But just do whatever works for you. Remember in what quadrant each of the functions, what's the sign of the functions in each of the quadrants. Okay, guys, I'm gonna stop here, and then I guess on Thursday we continue. And everything that we discussed for sine and cosine, they apply now with reference angles and all of that business. All right, any questions? Okay, so stop recording. And this is just continuation of the 6 trigonometric functions of discussion. So let me just, to have it fresh here, let me remind you. So recall, and if theta is any angle, then, and remember, if you want to think of theta as being a real number, then you need to consider the angle in radians, okay? So it could be any angle, but then it could also be any real number. So then tangent of theta, we define this as sine over cosine. Cotangent of theta, we define it to be cosine over sine. And then secant of theta is 1 over cosine. And then cosecant of theta is 1 over sine. Okay? So similarly, if instead of an angle you have a real number, we can talk about the same thing. Tangent of a real number is sine over cosine. And remember, the point of view is, if you talk about the angle, let's see, just to remind you of these ideas. So when we talk about the angle, here is the unit circle. Then if you talk about the angle theta, that's this guy right here. But if you think of theta as a real number, remember that is the arc length right here. Let's call it T. So because this is the unit circle, by the arc length theorem, as you know, T is going to be equal to the radius times the angle in radians, but the radius is 1. So arc length theorem then tells us that you can think of theta as a real number. It's the same thing as saying T, okay? Let me do it the other way around. T equals theta in radians, okay? In radians, this is very important. So theta has to be in radians. So this allows you, this connection then allows you to talk about the sine, cosine, tangent of real numbers, okay? Because we can think about real numbers in this way, just the wrapping function around a circle. Any number that you give me, you can think of that as being a little string of that length, and then you just start at this point, and then you wrap it around. If it's a positive number, you wrap around this way. If it's a negative number, you will wrap around this way, okay? And wherever it stops, that defines a point on the unit circle, and then you can talk about sine, cosine, and all of that business. Okay, so this is just a quick reminder of the things that we have discussed so far, and we talk about the values of all of these functions for the special angles, 30, 45, and 60, and also the quadrantal angles, 0, 90, 180, and 270, okay? All right, so again, this is just a summary. And we closed last time with the statement that all the previously known results, for sine and cosine, they apply directly to these other trigonometric functions. In particular, the notion of where they are positive and negative, they extend nicely this way, okay? Since we already know where sine and cosine are positive and negative, then immediately we know where tangent, secant, cosecant, and cotangent are positive and negative. And the summary is that in quadrant 1, everybody is positive. In quadrant 2, only sine and therefore cosecant are positive, the rest are negative. In quadrant 3, you only have tangent being positive, and therefore cotangent, the rest are negative. And in quadrant 4, we have cosine is positive, and therefore secant is positive, the rest are negative. And then we stop right there. I just want to continue right here, okay? All right, so the next thing is what's the relationship between the value of these functions and of an angle and the reference angle, and the result is exactly the same as the one that we had for sine and cosine. So let me write that theorem. So theorem, let's suppose that we have any angle, so let theta be an angle, and suppose that alpha is reference angle. So remember, reference angle, there is only one. Given an angle, what's a reference angle? It's the acute angle that we make with the terminal side of theta and the x-axis, okay? So that's alpha. So let alpha be an angle, and let theta be an angle, and alpha is reference angle. Then we have the following. So sine of theta, cosine of theta. We already know that. I'm just putting those here for completeness. So let's put tangent, then cosecant, secant, and cotangent. Okay, and then the result is, as we know, the sine of theta is the same thing as plus or minus sine of alpha. Cosine is plus or minus cosine of alpha, but then the same extends to the others. Okay, it's going to be plus or minus tangent, plus or minus cosecant of alpha, plus or minus secant, and plus or minus cotangent. And how do we determine whether it is plus or minus? Well, it depends on the quadrant, okay? Depending on the quadrant that theta lies, you will know whether the corresponding function is positive or negative, and then you pick the sign accordingly. All right, questions on this? So let me say here where the plus or the minus is selected depending on the location of theta, depending on the location of the angle theta. And by location, remember, it is whether it's in quadrant 1, 2, 3, or 4. Okay? All right. Questions on the statement of this theorem? Now we're going to do an example. Do you understand this? Okay, Ramses, don't worry. Okay, good. So I was just doing a summary of what we did last time, so you haven't missed nothing new. The only new thing that I've written down is what you see right now on the screen. Okay, so let's do an example. So example, I'm going to give you an angle, and then I want you to find all 6 trigonometric functions. Okay? So find, and of course, this is without using a calculator, right? So find all 6 trigonometric functions for the given angle. And let's see. First, let's do theta equals -5 pi over 6. Okay, so we have this angle, -5 pi over 6, and our job is to find all the trigonometric functions. Okay, so we need to know sine, cosine, tangent, all of that. Okay, so as the previous theorem suggests, if you want to evaluate any of the trigonometric functions at a given angle, the first thing that we should know is, first of all, we should know the quadrant in which this angle lies, because this way we'll be able to know whether the answer will be positive or negative. And then second, we need to know the reference angle, because remember, we always reduce all of these to the quadrant one situation, which is the reference angle. Okay, and then hopefully this would be an angle that we know. This would hopefully would be one of the basic angles. Okay, so first let's try to figure out in what quadrant is this angle. Can anybody tell me what quadrant this angle is? I'm gonna draw a little picture of it. Let's see, it's a negative angle. So what does this mean? Should we move clockwise or counterclockwise? How do we move? Do we move in the clockwise direction? That would be, this is clockwise. Or do we move counterclockwise? Red is clockwise, blue is counterclockwise. Very good, Emily and Sarah. So we're gonna move clockwise, right? Because the angle is negative, so that means we need to go in the red direction. And clockwise means, remember, in the sense of the clock. Okay, so as a negative angle, so we go clockwise. Where do we stop? So where do we stop? One easy way to see this is, well, let's divide, 5 over 6. 5 over 6, notice that this is going to be 0 point something. And what is this? So let's see, 6 times 8 is 48. So it's like 0 0.8 something, right? So 0 0.8 is something. You can just quickly divide it. 0.83333, etc. The point is that it's more than 0.5. Okay, so if this is 0, I'm going to be talking in terms of negative values. Okay, if this is 0, then here we're going to have negative pi over 2, right? Because we do pi over 2 this way, but it's negative. Then another pi over 2, here we have negative pi. Then here we're going to have negative 3 pi over 2, and then we're back to negative 2 pi. That's how you complete one full revolution in the negative direction. Does everybody understand what I'm writing? Do you understand this? Okay, so remember, if you want to talk about these angles in the positive sense, then negative 2 pi is just 0, negative 3 pi over 2 is just, the regular pi over 2, if we're talking in the positive sense, and so on. It will just be pi, etc., etc. Okay? So, no, we are not going to divide. Remember, when it's radians, we actually add or subtract. Okay, so we'll see. Let's first take a look at what's going on. Okay, so this number is negative 5 pi over 6 because 5 over 6 is 0 0.8 something. That's between 0 and negative 1. Okay, so it's more than negative 0.5, but it's less than negative 1, or actually, okay, the other way around. It's bigger than negative 1, but smaller than negative 0.5. So here is negative pi. Here is negative pi over 2. So I'm talking about this quadrant right here. Okay? And then we're going to have that number in here. Negative 5 pi over 6. Because remember, this is negative 0.5 pi. And, well, the other one is negative 1 pi. So this is negative 0.83. Repeated the 3 and then pi. So this is going to land in this quadrant, and that happens to be quadrant 3. Okay? So in the negative direction, you would say, oh, it's quadrant 2 because it's 1 and then 2. But in the usual sense, we call this quadrant 1, quadrant 2, 3, and 4. So we're going to be in quadrant 3. Okay? So that's the first thing that you need to be able to figure out in what quadrant this angle is. So right here is our theta. Okay? All right. Questions about the location of theta. I'm going to leave this picture here for reference. Questions about the location of theta. Okay, so Sarah, all we're looking at is in what quadrant this angle is going to be. This angle is negative 5 pi over 6, right? So we know that we need to measure clockwise. Now, the question is, where do we write the terminal side? Okay, well, just figure out what that number is. When you put your angles, these are negative angles, so that's why these values that you see here, are negative, just to have some reference, okay? So we have 0, then negative pi over 2. We are moving clockwise, okay? So 0, negative pi over 2, negative pi, negative 3 pi over 2, and back to 0, which is the same thing as negative 2 pi, 1/4 revolution in the clockwise direction. Do you understand this? Okay, so now we want to figure out where is this angle. And one way to do this is to look at the number negative 5 or negative 5 pi over 6 and see where it is, okay? So think about the real line now. Here is 0, here is negative 2 pi to the left, and we're basically splitting this into 4 pieces, right? Those are the 4 quadrants that we have. So here we have negative pi, so negative pi over 2, negative pi, negative 3 pi over 2, and then negative 2 pi. Are you following this? Okay, so our job is to figure out where is theta, in which of these 4 quadrants will theta lands. So one quick way of doing that is look at the coefficients, the 5 over 6, and divide it. When you divide 5 by 6, you get 0.833333 non-stop, right? Just take your calculator and do 5 over 6. You're going to see that. You could also realize that, this is less than 1 because 5 is less than 6. So what that means is, so far, because 5 over 6 is less than 1, we have a number on this part right here, because this is going to be bigger than negative pi. Remember that when we talk about negative numbers, the smaller it looks, the bigger it is, right? Like negative 2 is bigger than negative 10, because negative 2 is further to the right. Okay, so it's somewhere to the left, to the right of negative pi. Where is it? Well, 5 divided by 6 is 0.8333. That's actually bigger than 0.5, right? But remember, we're talking about negative numbers. So this is negative 0.5 pi. So where is negative 0.8333? Somewhere in here, right? Negative 0.8333. All of this is with pi, so I'm going to put the pi here. So that's how we know that it lands between negative pi and negative pi over 2. So that is this quadrant right here. That's all we're doing right now. Okay? That's all we're doing. Figuring out in what quadrant it is. All right, no problem. Is everybody else clear on this? How to determine that is in quadrant 3? Okay, perfect. All right, so let me get these things so they're not in the way. I'm gonna leave the picture above. Actually, I like this picture better than the one above, so let me use the second picture of the number line. Put it here. And just say, this guy is our theta. Okay, so now that we know that it's in quadrant 3, so theta is in quadrant 3. We know the quadrant, so this will allow us to know what are the sign of any of the trigonometric functions, okay, whether they are positive or negative. So now we know it's in quadrant 3. The next thing that we need to figure out is what is the reference angle, okay? So the good thing about the picture is that the picture tells you how to find the reference angle. Remember, by definition, this is the reference angle, right? So the reference angle is this one right here. Now, you can do this in different ways. How can you find alpha? You have to be careful because this is a negative angle now, okay? But you can reason through this geometrically. We can find the reflection of this, okay? So if this theta here was negative 5 pi over 6, then what would be this green angle that I did here? The reflection in such a way that this here is still alpha, okay? So what would be the green angle in this case? Remember, all I did was a reflection, so that means the same way that you move here clockwise, you just have to move it counterclockwise to find the reflection, okay? So if theta is negative 5 pi over 6, what's the green angle that I have here? It would be positive 5 pi over 6. Does everybody see this? Okay, and why am I doing this? Because now, since we have a positive angle, we can easily use the reduction formulas that we have, okay? So if you want to find alpha, what do we really need to do? All we have to do is do 180, or pi in this case, minus 5 pi over 6 to get alpha. Is this clear? So alpha, how do we get alpha? Well, the whole thing is pi, right? So that's going to be equal to pi minus 5 pi over 6, okay? And this is going to be pi over 6. So the reference angle, alpha, is pi over 6. Questions on how we found the reference angle? Because remember, the formulas that we study, the reduction formulas, they were assuming that the angle was positive. That's how we came up with the formulas, assuming that the angle was positive. So you have a negative angle. Once you have the picture, you know, all you have to do is flip the picture so that it becomes positive, and then you will be good to go. You can use your formulas. If not, then you have to reason through it by looking at the picture, okay? Just knowing what it is, you have to figure out what this alpha is, but remember that alpha is always positive in quadrant 1. So that's why I always reflect it. Okay, are you guys good with this? All right, so now that we have the reference angle, then we can find everything. Notice that pi over 6 is one of our basic angles, one of our, you know, the special angles that we need to know all the values. So we don't need a calculator to answer this question, so we can do everything. So now we can answer the sine, cosine, tangent. Well, let me put the negative 5 pi over 6. Cosine of negative 5 pi over 6. Tangent of negative 5 pi over 6. And then once we know this, then we can easily find cosecant of negative 5 pi over 6, secant, and cotangent. So my advice to you is always find these first three, sine, cosine, and tangent, because then the other three are very easy to find. So if we want to do sine of negative 5 pi over 6, how do we do this? First of all, we need to replace this by its reference angle, which is pi over 6, right? So this is sine of pi over 6. But then we need to decide whether the answer will be positive or negative. So in what quadrant is the angle theta, negative 5 pi over 6? In what quadrant did we say that the angle was? Is there? Another tricky question. It's in quadrant 3. So what do you know? So remember, with Ramses, we're talking about theta, right? Not alpha, but theta. Okay, so theta is in quadrant 3. So what do we know about sine? Is it positive or negative? In quadrant 3, what sine is negative? So sine of negative 5 pi 6 equals negative sine of pi over 6. You okay with this? And now what's sine of pi over 6? As you all know, pi over 6 is 30 degrees. So this is 1/2. So we get negative 1/2. That's the value for the sine. Now we do something similar for cosine. We are in quadrant 3. So what do we know about cosine quadrant 3? Is it positive or negative? Are we expecting here a positive or a negative for cosine? Negative. So this is minus cosine of pi over 6. And what's the cosine of pi over 6? That's square root of 3 over 2. Okay. And then finally, tangent. So let's see, what do we know about tangent in quadrant 3? Is it positive or negative? So remember, tangent is sine over cosine, because both of them are negative. When you divide them, you're going to get positive. And remember, we said last time in quadrant tangent is positive. So we're expecting a positive answer. And how do you find it? Well, just divide sine over cosine. So this is going to be negative 1/2 divided by negative square root of 3 over 2. So what do we get here? We get 1 over the square root of 3, because 2's cancel, which would be square root of 3 over 3. Questions about these first 3 values? Okay, and now to get the other 3, what do we do? Instead of using this reference angle business, remember, what do we know about cosecant, secant, and cotangent? They are the reciprocal of sine, cosine, and tangent, respectively, right? So you already have the first 3 values. All you have to do is flip them. Remember, cosecant is 1 over sine, so it's the reciprocal. So if sine is negative 1/2, then cosecant is going to be negative 2. If cosine is negative square root of 3 over 2, then secant is going to be negative 2 over the square root of 3. And similarly, if tangent was positive 1 over the square root of 3, I'm looking at this intermediate one here, then cotangent is going to be square root of 3. Just flip it. Okay? And with this, we found the others. Okay, questions? Yeah, so if you rationalize, this would be negative 2 square root of 3 over 3. If you rationalize that. I didn't rationalize it, so you will see that we are indeed flipping. So as you can see that all you do is, once you have cosine to get secant, what you do is you flip the value for cosine. And also the other way, if you know secant, you flip it and you get cosine, right? Okay. Questions? Okay. How about, let's see, try this one. Let me give you one for you to try. How about theta equals negative 7 pi over 4 minutes to work on this one. For this angle, find all the trigonometric functions. And remember, do not use calculator, okay? Do it by hand like we just did. You first need to figure out the quadrant that it is, then find the reference angle, and then you can write down the solutions, the answer to all the functions, okay? So let me put here sine, cosine, and tangent. And remember, once you know these 3, then the others are straightforward. Yes?
Professor, can you repeat, please, how did you get cotangent?
Oh, just flip tangent. Remember, cotangent is 1 over tangent, right? If you remember the reciprocal identities. So how do we define cotangent? Cotangent is cosine over sine, right? Let's see. So remember, tangent is sine over cosine, and cotangent is cosine over sine. So basically, what's cotangent? is what you get if you flip tangent. So here in the reciprocal identity, you see that cotangent equals 1 over tangent, right? Do you understand this? Okay, so in the example that we were doing, we already knew tangent, which was 1 over square root of 3. I mean, the final answer that I put was the rationalized version, but that's why I said let's look at this in between step, the one before the final version, right here. You see, tangent is 1 over square root of 3. So what's cotangent? You just flip that and you get square root of 3. You understand what I mean when I say flip? It's just, find the reciprocal. Of course, if you work with this one, it's the same thing. But when you flip it, you get this. But then if you rationalize, what do you get? 3 square root of 3 over 3. The 3's cancel out, so you get your square root of 3. It's just that it's faster to look at, since we already have the 1 over square root of 3, it's faster to look at that instead of doing all of this business. No problem. Okay, all right, so now do this, but for negative 7 pi over 4. I'll give you 3 minutes. Okay, let's see. So, can anybody tell me, remember, we first need to figure out in what quadrant this angle is. Can anybody tell me what quadrant this is? Very good. Does everybody understand that this is in quadrant 1? So this is in quadrant 1. Great. Do I need to explain this to anybody, or you guys are okay with this? Because that's the key. Once you know the quadrant, then the rest follows very straightforward. Okay? So, you draw a little picture. What is the angle? So the angle is going to land in here. So if you do, this will be your theta. Okay? Negative 7 pi over 4. Notice that this is 7 divided by 4. That's more than 1.5, but it's certainly less than 2. Remember that this one was negative 3 pi over 2, so that's negative 1.5. So if you think about the location, remember exactly what we did last time, the previous example. then negative pi, negative 3 pi over 2, because negative 3 pi over 2 is the same thing as negative 1.5 pi, then 7 divided by 4. So you will see, if you do the reflection, it's very simple. But if you draw the picture, it's even simpler than that, Maria. So you're going to see. So it's negative 1.5. So 7 divided by 4 is 1 point something, but it's bigger than 1.5. You can just quickly do the division. You get 1.75. So that means it's going to be, somewhere in here. In fact, it's exactly in the middle, right? Right here is negative 7 pi over 4, because this is negative 1.75. Okay, so it's in that quadrant, and as you know, in this picture, this represents, so this one represents quadrant 4, that's this one right here, right? Then this one represents quadrant 3, that's this one right here. This one represents quadrant 2, that's this one. And then finally, this one represents quadrant 1, which is this one. So is everyone okay with how to figure out the location? Now we'll talk about the reference angle. Okay, so we have the location down. Now in the picture, what's the reference angle? The reference angle is just this guy, right? So look, you can just think about it this way. The angle theta, what's the angle? The angle is negative 7 pi over 4. So according to the picture, all you need is to complete the revolution. So what are you missing to get to negative 2 pi? So what are you, so I'm talking in terms of negative values, right? Because we are moving clockwise. So what do you miss? What are you missing here to be able to complete your revolution? You just need an extra pi over 4, but in the negative direction, right? So if you move an extra pi over 4 this way, then you will get negative 8 pi over 4, which is negative 2 pi. So if you look at the picture, you can see it right there. Just like before here, for example, what are we missing in here? If you ignore the reflection that we did in this picture, what are we missing to complete the half revolution? So that's what alpha represents, what we are missing. Well, we already have negative 5 pi over 6. If you do an extra pi over 6 in the negative direction, you will get negative 6 pi over 6, which would be your negative pi, right? So that's how you know that alpha is pi over 6. Remember, alpha is always positive, so you still have to take the absolute value. So you can reason through it this way, or you can use the formulas. How? By reflecting. For example, here you could also use the formula. If you don't like to think about it this way, by saying, oh, what am I missing to complete the full revolution? Well, flip the picture, okay, in such a way that you keep here the same angle alpha. So, and remember, flipping the picture just means that if your angle was negative, you make it positive. So now this green angle here is positive 7 pi over 4. Do you understand this? I'm just flipping the picture. Do you guys see this? All right, and now where are we? We are in quadrant 4, and you can use the formula. What's the formula for quadrant 4? 7 pi over 4 plus alpha equals 2 pi. So what is alpha? 2 pi minus 7 pi over 4. And when you subtract this, what do you get? That would be 8 pi over 4 minus 7 pi over 4, which is pi over 4. So, different ways of looking at it. If you draw the picture, you can reason through it and say, well, I just need an extra pi over 4 to complete my revolution, so that's my reference angle. Or you flip it to get the positive version, and then you use the reduction formula that we discussed last time. So regardless, the reference angle is pi over 4, right? It's in quadrant 1, and reference angle alpha is pi over 4. Everybody okay with this? And how to find the location and the reference angle? Okay, good. All right, perfect. And so now that we know the reference angle, then we can ask the question, right? So it's in quadrant 1. So what do we know? What are we expecting about all of these results? What do we know about the sign? In quadrant 1, when an angle lies in quadrant 1, what do you know? Everybody's positive, right? So this would be the same thing as sine of pi over 4, cosine of pi over 4, and tangent of pi over 4, right? Everybody's positive because we're in quadrant 1. Okay, what's the sine of pi over 4? Remember, pi over 4 is 45 degrees. What's the sine? Remember that you're expected to know this, right? So square root of 2 over 2. What's the cosine? It's the same, square root of 2 over 2. And therefore, if sine and cosine are the same, what's tangent of pi over 4? Equals to 1. Good. And now to get the other 3, all we have to do is flip, okay? So cosecant is going to be 2 over the square root of 2, which then give you square root of 2 when you simplify. Secant will give you the same thing, right? Square root of 2. And then cotangent, you flip the tangent, so you also get 1. Okay, questions? All right, perfect. So again, of course, you know, if the angle that you're given is an angle that is not any of the special angles that we have discussed, then you know you use your calculator at that point. Once you figure out your reference angle and so on, then you put in your calculator and then it will tell you. But if you are asked these questions, it will be angles that you're expected to know. Okay, like the 45, 30, or 60 degrees, or any of the quadrantal angles. Okay, so now that we have discussed this, then let us take a look more closely at the trigonometric functions as functions, okay? And let us see some properties that they enjoy. In particular, I want to discuss the notion of symmetry of the trigonometric functions, okay? And for example, notice that here, let's see. Yeah, in here it may not be straightforward to see because we have the cosine. But okay, anyways, let me just talk about the symmetry, and then we're gonna go back to this example that we just did, and then I'm gonna make some associations to them. Okay, but let's first talk about symmetry. Okay, so first of all, and I guess my first question to you is, do you remember what this is? So what do we mean when we say symmetry of a function? So recall symmetry of functions. Does anybody remember what this is? So remember, when we say symmetry, we mean even and odd functions. Do you remember this back from college algebra? Kind of, barely. Okay. All right. So remember, symmetry is this idea of that the graph of the function kind of looks nice. So we have two types of symmetry: even and odd functions. A function is even if the graph is symmetric with respect to the y-axis. The classical example is, you know, the parabola, y equal x squared. This is an even function because the y-axis acts like a mirror. If you fold the graph along the y-axis, the two pieces will overlap. Is this coming back to you? Do you remember this? No? Still foggy? Okay, more or less. All right, so this is what it means to be even, symmetric. Now I'm going to formalize this, symmetric with respect to the y-axis. The other notion of symmetry that we want to discuss is the notion of being odd, okay? So what does it mean to be odd? Well, the classical example is the x cubed function. So this is how x cubed looks like. And basically being odd, it means the following. It means that you are symmetric with respect to the origin, with respect to the point 0, 0. So what that means is that if you take one piece of the graph, for example, let's take the piece in quadrant 1. and you flip that one with respect to the x-axis, you get this, and then as a result you will obtain an even function. In other words, if you flip half of the graph and then you fall along the y-axis, the two pieces will overlap. So if you flip this part and then you fall, the two pieces overlap. Okay, so that's what it means to be symmetric with respect to the origin. So algebraically, what does that mean? If I take a point on this graph, okay, let's say that this point has coordinates x comma y, because this is symmetric with respect to the y-axis. What does this mean? It means that if I go horizontally this way, the y-axis acts like a mirror. So that point is going to have a partner, but that partner is going to have the same y because we're doing it at the same level, right? But notice that the x is the opposite sign, so negative x comma y. So that's what it means to be even. If x comma y is on the graph, then negative x comma y must also be a point on the graph. Okay? So that's what it means. In other words, you think about it, it doesn't matter whether x is positive or negative, the y value is always the same. That's basically what it means to be even. And it's clear here because we have a square, right? This function doesn't care whether you plug in a positive or a negative x because a square kills it. Do you understand this? I'm gonna write the definition now, but so that you hopefully you don't forget this by looking at this picture. Now, well, so that's what we're gonna call even function. Okay. Now, what does it mean to be odd? Well, let's take a look at x cubed. In this case, if you plug in something negative, the negative survives, right? And basically, what it means is the following: if you pick a point, let's say x comma y, a point on the graph of the function, is gonna have a partner. But what's the partner of this guy? Well, you have to flip the y, and you need to flip the x to get your partner. In other words, if x comma y is on the graph, then negative x comma negative y would also be a point on the graph. Okay, that's what it means. That's what it means to be symmetric with respect to the point 0, 0. So if 1, 1 is on the graph, then negative 1 comma negative 1 will be on the graph. If 2 comma 8 is on the graph, then negative 2 comma negative 8 is on the graph. So why is this helpful? Because that means that if you already know half of the graph, if you already know this part, then by symmetry, you will get for free this other part. Okay? So symmetry helps you to actually graph a function. Okay? You only have to worry about half of the graph because the other half, you get it for free if the function is symmetric. And when the functions are not symmetric, we say that the symmetry is neither. Okay? All right, so this is what it means to be odd. So even if x comma y is on the graph, then negative x comma y is on the graph. Odd is that if x comma y is on the graph, then negative x comma negative y is on the graph. So another way of looking at this algebraically is as follows. So let me remind you the definition. Let's suppose that you have a function, let y equal f of x, be a function. Then, so what does it mean to be even? So f is even if, so notice that the condition here is that whether you plug in x, so I'm on my yellow, so whether you plug in x or negative x, okay, then you will always get the same y. By looking at the picture, that's exactly what we see. How do we write that algebraically? Well, if I plug in negative x, so here I'm talking about the y corresponding to negative x, this is the same thing as if I just plug in x, okay? So if you plug in negative x, you get back the same formula. If this happens for all x, that's what it means to be even. This right here is saying that if x comma y is on the graph, then negative x comma y is also on the graph. And now, on a similar note, what does it mean to be odd? So f is odd if, so notice, what are we saying here? This x right here has a corresponding y, namely y. And then what's the y of negative x? Well, the y of negative x is negative y. So the negative of whatever x has. So in other words, f is odd if the y corresponding to negative x is the same as minus the y that corresponds to x. In other words, we can factor out the negative out of the function, okay, for all x. This is what it means to be odd. And the classical examples are x squared for even. Basically, even means, we don't care whether the input is positive or negative. You will always get the same output. And odd means that if you have a negative input, then you can take the negative out of the entire function and factor it out. And that's classic. The classical examples are x squared for even and x cubed for odd. Do you understand this? All right, and so just for completeness, let me remind you here. So, and that means that the graph, so graphically, what is this? Graph of f is symmetric with respect to the y-axis, and this one means that the graph of f is symmetric. Can you see my screen? Because I think that the screen is gone. Okay, what happened here? Let's see. Oh, my tablet got disconnected. Why are you doing this to me? Oh, let me hopefully fix this. Last time it was the power. This time is the Wi-Fi disconnecting. There are strange forces behind the scenes. Yeah, but it was the tablet that disconnected. Like, I'm not sure what. Too much math for the tablet. Okay, give me 1 minute. It's trying to connect to Blackboard again. Okay, so let's see. It's supposed to be in. Can you guys see my screen now? Right, perfect. Okay, so even means that the graph is symmetric with respect to the y-axis. Odd means that the graph is symmetric with respect to the origin. So graph of f is symmetric with respect to the origin. So the point 0, 0. Okay. All right. So this is the question that we want to answer now for the trigonometric functions. So we have 6 functions. What's the symmetry of this function? Are they even? Are they odd? Or maybe they are neither? Okay. Of course, if a function is not even and is not odd, then we say that it's neither. Okay. So do the trigonometric functions enjoy some type of symmetry? That's a question that we want to answer now. So the question is, what is the symmetry of the trigonometric function? What is the symmetry of the trigonometric function? And this is because, of course, remember, we are analyzing these functions, so our job is to eventually be able to graph these functions. So we would like to be able to find the symmetry, because if they are symmetric, we just have to worry about a piece of the graph, and then the rest, we get it by symmetry, okay? So that's why it's important. So what's the symmetry of the trigonometric functions? And it will also allow you to, evaluate these functions more easier. Okay, so the first remark that I want to make is that it's enough to study sine and cosine. And the reason is because once we know what happens with sine and cosine, then we can translate this to the other 4 functions, because they are defined using sine and cosine, okay? And then it's just algebraically, we can easily see the results for the other 4. So right now it's enough to focus on sine and cosine. So enough to study sine and cosine. So what we mean by this is the following. So I'm not going to use x because x I'm going to be using it for points on the unit circle and so on. So I'm going to use t as an input, okay? So for any real number t, what we would like to answer is, what can we say about sine of negative t versus sine of t? And similarly, we would like to say something about cosine of negative t versus cosine of t, okay? This is really what we are trying to figure out. Because once again, notice that in both cases, whether it's even or odd, is always determined by plugging in negative x into the function and then seeing what happens to the output. If the output doesn't change, if it's the same as the original function, you get f of x back, it's even. If what you get back is minus the function, then it's odd. But notice that in both cases, you always plug in negative x. So that's why to understand the symmetry, we are going to analyze what happens when you plug in negative t versus plugging in just t, right? And then seeing, do we get the same thing or do we get something different? Do you understand what we're about to do? Okay, so as usual, there are several cases to consider, right? Depending on the quadrant that t is, remember, t is a number, but you can think of it as an angle, all right? Because we're working on the unit circle. So depending on the quadrant that t is, then we may be able to see something different. So we should be analyzing this. So let me say this. So the point is that once we do a couple of quadrants, then the others will be very similar. So we'll only do 2 of them, okay? So several cases. So case 1, t is in quadrant 1, right? The other 3 cases are quadrant 2, 3, and 4, of course. Okay, so let's analyze what happens if t is in quadrant 1. What can we say about this relationship? So let's draw a little picture. Okay, so we have our unit circle, 1, 1, negative 1, negative 1, and then we have our angle, which, remember, when you think of t as a real number, we are really talking about this right here, the arc length. But as you know, because this is the unit circle, we can also talk about this angle, okay? And the measure of that angle in radians will also be t. So here t is in radians. Okay, so this is the picture, and then, we have a point here. Let's call it P, and that point has coordinates x, y. And as you know, what is x? X is cosine of t, and y is the sine of t. Okay? All right, so then we draw a little triangle as usual. Then I'm going to get a little triangle here. And so let's look at the following picture. I'm going to go ahead and do the reflection of this, okay? Instead of t, I want to consider the circle with angle negative t, because remember, we are comparing negative t versus t. That's a picture for t on the left. Let us do the picture for negative t on the right. Okay, so it's a negative angle, so it's going to go this way. This is negative, but in absolute value, the angle is the same, right? So it's going to give me a point. I'm going to call it Q. And this Q, we have coordinates x, y, which are cosine of negative t, sine of negative t. Everybody following this construction so far? You guys okay with this so far? Okay. So our job, of course, is to say something about Q, about the coordinates of Q versus the coordinates of P. So how does the value of Q relate to the x value of P? How does the y value of Q relate to the y value of P? And we'll do the same thing that we did last time. A little triangle here. So these two triangles are equal, right? By the angle, side angle criterion. So remember, this is 1 and this is 1 because that's the radius. So the two triangles are equal. Triangles are equal by the angle, side angle criterion. And therefore, what can we say about the corresponding sides? The corresponding sides are equal, right? So what can we say about the coordinates of Q? Let's see. So the value of Q, the x value of Q, remember, which is this cosine of negative t, is going to be the same as the x value of P, right? It's positive. So that's still x. And what can we say about the y value? So what can we say? This right here is x. What can we say about this y value right here? In terms of P? Anybody? The triangles are equal. So that means that this side in the circle with P corresponds to this side in the circle with Q. So if the side for P is y, what will be the side for Q? This is going to be negative y. Very good. So that's x comma negative y. So moral of the story, what do we see here? Sine of negative t, which is the y value of Q, is going to be equal to minus y. So that's negative y. But remember, y is sine of t, so this is minus sine of t. Cosine of negative t, that's just the x value of Q, which is the same thing as saying cosine of t. So in quadrant 1, we see that sine of negative t is minus sine of t. Now let's ignore the in-between term. So let's ignore this part here in the middle. And then cosine of negative t equals cosine of t. So as far as quadrant 1 is concerned, what behavior do we have here? Sine behaves like an odd function, and cosine behaves like an even function. Do you see this so far? Remember, odd means that you can take the minus out. Even means the minus is gone. And that's basically what we see happening here. Okay? So let me make a remark. I want to tell you that similarly, we obtain this result. We obtain this if t is in quadrant 4. So we basically have quadrant 4 for free. And why is this? If t is in quadrant 4, you will basically have a picture like the one that we have on the right. Instead of negative t, when you put t, you will have a picture of the one on the right. It's just that t is going to be this guy. Okay? But it's basically the same picture. We'll be using the same angle anyways. Okay? And then negative t would be the picture that we have on the left. But once again, instead of being measured counterclockwise, it will be being measured this way, clockwise. But it will be the same picture, but we will have again the equality of the same triangles, so the same result will apply. The coordinates of P and Q will have the same relationship. Do you see this? That the two cases are similar? So there is no need to argue case 4, quadrant 4, because that's the same as quadrant 1. Okay? So in quadrant 1 and quadrant 4, we have this symmetry behavior. So how about the other important case, which is T in quadrant 2? Okay? In quadrant 2 was a picture. Let's draw it here. And in fact, here we can use the same picture for both situations to save time. So we are in quadrant 2, our unit circle, and then let's put T here. Let's say that this is T. We have a point here, P, comma Y. And remember, X represents cosine of T and Y represents sine of T. Now, what is it we're going to do? Well, we're going to do the reflection, right? So if you reflect this, you're going to get another point here. let's call it Q, and then this angle here, remember this is negative T. Just the same measurement, but instead of doing it counterclockwise, we're doing it clockwise, so you get the negative angle. And this Q, of course, it has coordinates, x, y. Our job is to figure out the coordinates of Q. Remember, the coordinates of Q are going to be cosine of negative t, comma, sine of negative t. That's Q. Okay, so let's see. Looking at the picture, again, by symmetry, this angle is the same as this one. Then we have the same reference angle. Therefore, this little triangle is the same as, let me change the color, as this triangle. These two triangles are equal. This is 90 degrees. So two triangles are equal. And because the two triangles are equal, then we can say something about the coordinates of Q. Who can tell me what's the coordinate of Q? Using the coordinates of P. Using X and Y, what would be the coordinates of Q in this case? Since these two triangles are equal. Let's see, will X be the same for both P and Q? So be careful, honey. If you say negative X, you're sending X to the other side. We already know that X is negative, right? If we're in quadrant 2, we know that X is negative. Very good. So, looking at the picture is straightforward to see. X is the same. So Q is going to be X, comma, and what's the Y value of Q? By equality of triangle, this Y value here in absolute value is the same as this Y value here. So if we have Y on top, then we're going to have negative Y in the bottom. Very good. Do you guys understand this? That this is the value of Q? These are the coordinates of Q? Yes or no? All right. So then from here, then we deduce. So Maria, what is it that's confusing? Again, the two triangles are equal, so that just means that all the sides are equal. The X, because by construction you can see this is by symmetry, right? So the X is the same. This side right here is common to both of them, so they have the same X value. So that should not be an issue. The question is, how about Y? The Y of Q is given by this piece right here, but that piece is the same as this one, right? In absolute value. If the one on top is a Y, then the one on the bottom will also be Y in absolute value, but because it goes down, it has to be negative Y, because it's a negative number, okay? So if you have Y up here, then you need to have negative Y down here. That's basically what we are saying. But now, what's X? X is the same thing as saying cosine of negative t, and what's negative Y? The sine of negative t. So we have the sine of negative t is negative Y, which is the same thing as minus sine of t, because Y represents sine of t, that's the Y coordinate of p. And similarly, cosine of negative t is just X, which is the same thing as cosine of t. So once again, in quadrant 2, we have this symmetry behavior that sine behaves like an odd function and cosine behaves like an even function. The only case that remains to study is quadrant 3, but again, that's just this picture, right? Just if you have an angle in quadrant 3, then you will get your P will be Q, right? You will have the blue picture, and then when you look at minus the angle, you will get the red picture, okay? So again, for free, we get the quadrant 3 result. So in a similar way, if T is in quadrant 3, we get the same behavior. So moral of the story, regardless of the quadrant, we always see that the sine acts like an odd function. You can take the minus out, and the cosine acts like an even function. So that's exactly what they are. Okay, so theorem that we just did above was the proof of this theorem. So that's the theorem, and this one is the one that tells you the symmetry of the trigonometric functions. I mean, you just have to remember the symmetry. You don't have to remember the proof, but you just need to know this result. Now, of course, if you ever forget, then you will know that all you have to do is play a little bit with the definition and some geometry, and then you recover this result. Okay? So symmetry of trigonometric functions, and then here is a statement. So for any angle x, we have the following. So remember, we are comparing sine of negative x, cosine of negative x, and what we just saw is that sine of negative x is minus sine of x. So the sine is odd, and cosine of negative x is cosine of x. The cosine is even. This is what we just saw. Okay? But now from here, we can immediately extend this to the other 6 trigonometric functions, the other 4. So let me just write down the extension. Tangent. So remember, what's tangent? Tangent is sine over cosine. Now on the sine, the minus goes out. The cosine, the minus is gone because it's even. So the minus survives as a whole. So this would be minus tangent of x. So the tangent is also odd. Okay. As a result, if tangent is odd, then so is cotangent, because cotangent is 1 over tangent. And if sine is odd, so it's going to be, oops, if you complain, why did it do 1, 2, 4? Okay, so 1, 2, 3, 4. Then the same thing is cosecant, right? Cosecant of negative x is going to be minus cosecant of x. The cosecant is odd as well. And finally, number 5, secant of negative x is minus secant of x. So moral of the story, among the 6 trigonometric functions, only the cosine and therefore the secant function are even. The other 4 are odd. Okay? So, ahí, cosine and secant are even. And then the rest, sine, and then the other, sine, cosecant, tangent, cotangent, are odd. Okay? So that's the moral of this theorem. But again, you get all of this by just analyzing sine and cosine. All right, so let me show you, now you ask me questions if you have, but let me show you how we can now easily use this. For example, let's look at the exercise that we saw before. Before we were calculating all the values of negative 7 pi over 4, right? That was the example that we did. Well, now we can actually take advantage of symmetry. So remember that secant is 1 over cosine. Oh, wait. This minus should not be here. Sorry. So secant is even. So, and in the formula, I had put a minus there that was not. Okay. Yeah. And the reason why it's even is because secant is 1 over cosine. So, for example, you have secant of negative x. This is the same thing as 1 over cosine of negative x. But cosine of negative x is just cosine, because cosine is even, and 1 over cosine gives you secant. That's how you justify number 5. And similarly, you justify this way number 4, number 6, and number 3. Okay? So the proof of 3 to 6, I'm going to leave it to you to play around with. This, for example, would be the proof of number 5. Okay? Using the properties of sine and cosine. The hard work is sine and cosine, and that's what we did above together. Okay, so for example, how can we use this? Well, let's say that you want to calculate sine of negative 7 pi over 4. Now you don't have to break your head with negative angles and trying to figure out what quadrant it is and the reference angle and so on. What you can do immediately now is use symmetry. So sine of negative 7 pi over 4, okay, the sign is odd, so you know that this minus, you can take it out, okay? So this is the same thing as saying sine of positive 7 pi over 4. So we immediately change the problem to the positive angle question. So what this means is that you don't have to worry about trigonometric functions of negative angles because you can always use the symmetry to turn the question into a positive angle. Okay? And now here you answer this. This is in quadrant 4, so we know that the reference angle is pi over 4. You can use, your formulas like we did before, and so we get a negative square root of 2 over 2. If you were doing cosine instead, well, you know that cosine is an even function. Let's wait for this. My tablet is acting weird again. Let's go back. I have to do something with the RAM memory or something. I don't know. When I use it too much like this with one note, it kind of starts to slow down, etc., etc. So if we want to do cosine, no Wi-Fi. Wi-Fi is good. I mean, if you stop hearing me, then that's the Wi-Fi that's gone because I'm using two computers, my desktop and my tablet. My desktop to talk and the tablet to write. Okay, so we have cosine of negatives, and also so I can see your chat because if I'm sharing my screen in the tablet. If I only use the tablet, I don't see what you're writing, and so since usually you guys don't talk, then it's very hard for me to see what you're saying. So it's easier to have the screen in front of me with the chat, and then I write here. Okay, that's why you see, two mysterious names. If you look at the attendance, I'm sharing my screen here. If you click on the attendance, you will see myself, and then there is a mysterious Luis Aumet tablet. Well, it's not mysterious because it's clear by the name, right? What it is. Okay, that was a commercial. Let's go back here. So if we want to do cosine of negative 7 pi over 4, now we can say, okay, cosine is even. That means the negative is not really important here. It's gone. So we can just ignore the negative. And this is cosine of 7 pi over 4. And we proceed as usual. Okay? So we know that this is in quadrant 4. And then in quadrant 4, cosine is positive. So that would be cosine of pi over 4, which is square root of 2 over 2. So I guess this symmetry business allows you to remove the headache of figuring out in what quadrant is your negative angle and what's the reference angle in that point of view. What we're doing earlier today, you can now avoid that, skip that, and use the symmetry instead if you like. But it's up to you. Anyways, regardless of what you do, you will get the same answer. Okay, any questions on this? Okay, so that's the symmetry of the trigonometric functions. We'll come back to this when we start talking about their graphs, okay? Another thing that I wanted to give you is the Pythagorean identities. Remember that we know one of those. We know the basic one, which is sine squared plus cosine squared is equal to 1, right? So the point is that there are two more, but basically they all come from this basic Pythagorean identity of sine and cosine. But let me give you all of them because you will need these a lot in calculus. In particular, in calculus 2, you're going to be using these identities left and right. And this is the point to learn what they are. Okay, so what are we going to need for this? So recall. So the definition of tangent, which is sine over cosine. Cotangent is cosine over sine. I'll take advantage of this. And also, the secant, which is 1 over cosine, and cosecant, which is 1 over sine. Okay, so remembering this, these are the quotient identities, and then on the right we have the reciprocal identities. Then we get what we call the Pythagorean identities. And it will be clear why, why they are called like this. You already know why the basic one is called like this, because it really comes from the Pythagorean theorem, right? The fact that you are a point on the unit circle. And that's the first one, number one, that says sine square plus cosine square. What is this? What is this equal to? Is equal to 1, right? So sine square plus cosine square is equal to 1. This is called the Pythagorean identity. And remember, the reason is because these are points, these are the coordinates of a point on the unit circle. So sine is the y, cosine is the x. So what we're basically saying here is y squared plus x squared is equal to 1. And as you know, this is the equation of a circle centered at the origin with radius 1. So this is just the unit circle. Okay, so of course every point on the unit circle satisfies this equation. So that's why the coordinates of the point, which is x comma y, which translates into cosine comma sine, they will satisfy that equation as well. Okay, so that was the reasoning, and we already discussed this earlier. Okay, so this is what we know. The point is that there are two more, and basically, they come from the identity that we have above. So what I'm going to do is I'm going to write the proof, and then we're going to come back and write actually the statement. So the proof of number one, we already did it. So number one is done before. Now, what's identity number two? Well, let's see. Again, all of this, the reason why I'm showing you this is because you don't have to memorize the three identities. I mean, eventually you will know them, but if you remember this one, sine squared plus cosine squared equals 1, then you can easily recover 2 and 3, which I'm about to write. Okay, here is what we can do. Okay, so we have sine squared plus cosine squared equals to 1. And what we can do is, well, nobody stopped me from dividing both sides by cosine squared. So let's do that. I'm going to divide both sides by cosine squared. If we do that, let's see what we get. Let's see. Of course, here we're going to get plus 1, right? Because the cosine squares are going to cancel out. Now, what do we get in the first term? What's sine squared over cosine squared? That's the same thing as saying sine over cosine squared, and you should realize that that's the same as tangent squared, right? And then what do we get on the right? We have 1 over cosine squared. That's the same thing as saying 1 over cosine, all of that quantity squared. So that is secant squared. So here is another version of the Pythagorean identity. If you do tangent squared plus 1, you're going to get secant squared. Okay? And similarly, what is number 3? Well, you have sine squared plus cosine squared equals to 1 again. But this time, instead of dividing by cosine squared, nobody stopped me from dividing by sine squared, right? Let's do the same thing, but let's divide by sine squared and see what we get. So if we divide by sine squared, what do we get? So in the first term, we get 1, right? Because the signs cancel out. Plus, what's cosine over sine? That's cotangent, but this time it's going to be cotangent square because of both of them are being squared. And then 1 over sine, what is this? That's cosecant. Okay? So 1 plus cotangent square equals cosecant square of theta. So these three guys are known as the Pythagorean identities. We're going to be using this later on in the course when we discuss trigonometric identities in general. But when this is going to be really needed for you, it's going to be in Calculus 2. Okay? Once you, those of you that need to take Calculus 2, when you talk about integration, you're going to be using, for trigonometric integrals, you're going to be using these identities left and right a lot. Okay? All right, so that's these are the Pythagorean identities. Are there any questions how we obtain these formulas? Did you understand this? Okay, and I want to show you that actually in rare instances you will use them in this form. As we already experienced with the first one, with number one, instead of using it like that, usually we use it in its two variations, right? What are the two variations of number one? We can write this as sine squared is the same as 1 minus cosine squared. And similarly, cosine squared can be written as 1 minus sine squared. These are the two variations of number one. And, usually we use them in this form. You can think of this as a way of writing sine in terms of cosine. That's the first one. And the second formula is a way of writing cosine in terms of sine. Okay? So if you ever need to get rid of this of sine, this is what you can do. If you need to get rid of a cosine, this is what you can do. Now, similarly, number two then give you another one. The same way that tangent squared plus 1 equals secant, then you gain the fact that tangent squared can be written as secant squared minus 1. So this is a way of going from tangent to secant, taking an expression that only has tangents and turning those expressions into secants. Okay? And similarly for number three, this means that then cotangent squared is going to be cosecant squared minus 1. Okay, do you guys have any questions on this? Questions? All right. And by the way, so you see that I'm not lying to you. Let's see, let me show you, just so you can see that this will indeed be used. Do I have my, here, Calculus 2 Spring 2020. This was when I taught Calculus 2 back in the spring. Let me just show you where these formulas are being used. Okay, so here we have trigonometric integrals. We're going to be doing these things later on, like how to take something like cosine to the 4 and writing this expression. Okay, this right here, this is trigonometry. That's not calculus yet. Okay, we will discuss this at some point. But you see, here are to answer integrals about powers of sine and cosine, we have to use, you see, the Pythagorean identities. Okay, for sine and cosine, they will be very important for us. And then when you talk about trigonometric integrals involving product of secants and tangents, so I'm not sure what that means. Where are the? Oh, that meant that there was a substitute in the class that day. Yeah, I remember. I couldn't teach that day, and then somebody else went and did the class. But then when I came, I did some examples, and let's see, this was for cosine. Did I say anything about tangent? Yeah, since the substitute did that day, then I didn't actually cover the theory, but in the examples you can see, for example, here, how in solving the integral, we use the fact that we have a tangent square, and then that tangent square, we wrote it as secant square minus 1. And then, we continue with that and doing all stuff. You don't have to worry about what's happening here. All I'm trying to show you is how what you're learning now will be used later. Okay? Those kind of identities. For example, over here we used it again. You see, tangent square, it turned into a secant square, -1. Okay, and that makes the problem easier to solve later on, and so on and so forth. Okay. All right. Anyways, this was just to show you that this is going to be used. Okay, when you study calculus 2. So it's not meaningless. Okay. Anyways, let's get back to our business right now. All right. Any questions up to here? Any questions? Okay, good.